Hello, my name is David Ivan Villalba Mejorada. I'm a PhD student in Advanced Technology at Instituto Politécnico Nacional. My research is called hollow microcubes of zinc cobalt hexafluorides to obtain a 2.1 volts hybrid supercapacitor in neutral adherence electrolytes. We start from the main problem. The energy crisis and environmental issues have increased dramatically in the last year due to the continuously growing demand for electric energy, which is challenging for humans to achieve sustainable development with clean energy. Hybrid supercapacitors improve energy and power densities by combining supercapacitors and batteries electrodes characteristics. Prussian blue analogs (PBAs) form a large family of coordination polymers with an open framework, with interesting characteristics such as cathode materials for energy storage due to their redox process. In the present world, a series of hollow PVA cubes were synthesized using a template to improve the stability and the contact surface area of an assembled hybrid supercapacitor. A series of materials with different cobalt zinc molar ratios were synthesized. This is cobalt hexafluoride, 3 cobalt zinc hexafluoride, cobalt zinc hexafluoride, cobalt 3 zinc hexafluoride, and zinc hexafluoride respectively. It's important to say the cobalt incorporation increases the material's energy storage capacity, while the zinc promotes an increment in the potential for redox process. Subsequently, the material of interest is precipitated with the molar ratio mentioned above on the template. It was allowed to stir for 12 hours and then the temperature was increased to 60 degrees Celsius, stir for another hour, and finally the material is washed and dried. Figure 1b shows the scanning electron microscope study, showing the variation in morphology resulting from the molar ratio and the stability provided by the increase in cobalt in the material. Figure 2 corroborates the formation of the hollow cubes by the transmission electron microscope and EDS elemental mapping techniques. It can be clearly seen that the incorporation of zinc in the sample is congruent, resulting in highly structural stable materials with the corresponding molar ratios. Similarly, X-ray diffraction and infrared studies were performed, which are shown in Figure 3a and 3b, respectively. Firstly, the X-ray diffraction patterns are obtained, showing a cube phase in the materials that contain the mixture of metals, cobalt, zinc, or only cobalt. In infrared, the characteristic signals of the CN bond are observed with different shifts corresponding to the oxidation state of the materials. It is also observed that this is not a residue of the template in the material. Once the spectroscopic characterization was complete, we evaluate the materials electrochemically in 3 electrode cells. Starting from the cyclic voltammetry technique shown in Figure 4a, the contribution of the redox pair of the materials is observed depending on the cobalt-zinc molar ratio. At a speed of 1 millivolts per second, this gives the opportunity to study the world area of the material. Understanding that the more area we have, the more load to material can store. The materials without the molar ratio used to be the ones that contain the last exploration area and low current, while the work potential is maintained in all materials. Figure 4b shows the galvanostatic charge and discharge profile of each one of the materials to select the best material of the series. As can be seen, the material with the highest capacity is 3 cobalt zinc hexafluoride, which is 88 milliamperes per gram, while zinc hexafluoride has the lowest capacity. On the other hand, the current versus capacity profile shows once the cathode was evaluated, the best material was selected, the complete system was evaluated, having an activity carbon as a counter electrode to have the configuration of a hybrid device. It is assembled and evaluated by means of cyclic voltammetry shown in figure 5a at 10 millivolts per second, resulting in a stable electrochemical fingerprint at a voltage of 2.1 volts in combination with the two electrodes. The study of the galvanostatic profile of the device shown in figure 5b was performed. The hybrid device achieved a specific capacitance of 59 farads per gram, 0.5 amperes per gram. Approximately 63.3% of the capacitance was maintained even at a specific current of 10 amperes per gram, indicating good rate capability. Figure 5c shows the Dragon plot giving the specific energy power of the hybrid device. It is promising that the cell delivers high specific energy of 30 watts-hour kilogram at a power of 450 watt-kilogram. Specific energy values of 7 watt-hour kilogram are still being obtained even at a high specific power of 5.5 kilowatts per kilogram. This behavior suggests that the specific energy of this hybrid device was quite acceptable, and the energy power characteristic makes a hybrid supercapacitor suitable as a low-cost device of large-scale energy storage application. Once the results of the device are known, the electrochemical impedance spectroscopy and the cycling stability are finally evaluated. Figure 6a shows a schematic representation of the hybrid device. The schematic shows the electrode of Faraday-type material, in this case 3 cobalt zinc hexafluoride on the right side, and the electrode of capacitive-type material, active carbon, on the left side, reaching a voltage of 2.1 volts in a fully charged state. The equivalent electrical circuit involves components representing the electrode's contribution to the hybrid device's impedance behavior. The negative electrode of the left side is the carbon, where the diffusion part is not present in the equivalent circuit. The right side shows the contribution of the positive electrode, cobalt zinc Prussian blue analogs, which includes the diffusion of the charge compensating ions inside the solid. R sol represents the solution resistance between the two electrodes and the storage capacity, C store in this case, of the whole device is expressed as a contribution of the carbon and the Faraday electrodes. Figure 6b shows the experimental Nyquist plot for the hybrid supercapacitor at a fully charged state and after several galvanostatic charge and discharge cycles. The plot shows the typical behavior expected for a supercapacitor. One, a high frequency semicircle associated with the resistance of the paste in the electrode and the capacitance of the dielectric employed to integrate the past Teflon. 2. A continuous increment of the imaginary and real impedance associated with the diffusion of the charge compensating ions in the positive electrode. 3. A final vertical increase of the imaginary impedance associated with the charge accumulated in the electrode through the double layer in the carbon, charge transfer, and potassium ion insertion extraction in the cobalt zinc hexafluoride. The long-term stability during the cycling of the hybrid device shown in figure 6c was evaluated by charge-discharge measurement at a current density of 6 amperes per gram after 5,000 cycles. The hybrid device retained 85% of its initial capacitance, black line, indicating good cycling stability since a battery electrode is employed in the hybrid device. Furthermore, Coulombic efficiency, red line, was maintaining at approximately 96.2% during cycling test, suggesting that the device did not suffer a significant side reaction that might induce the degradation of the electrodes. The capacitance values are plotted in figure 6C blue line, indicating that the device storage capacity has a stable trend with a slight decrease during cycling as measured from galvanostatic charge discharge. In the same way, another relevant parameter is the series resistance of the device, green line, equivalent series resistance. The continuous increment of the equivalent series resistance indicates that capacitance loss during cycling may be related to the electrolyte resistance increment, probably caused by the insertion-extraction process of the potassium ions in the positive electrode. In conclusion, cobalt zinc hexafluoride hollow cubes were obtained by the co-precipitation route using manganese hexafluoride as a template. Transmission electron microscope characterization confirmed the formation of hollow structures and the presence and homogeneous distribution of zinc in the solid. The incorporation of zinc into the cobalt hexafluoride caused the rounding of the edge together with the apparent large surface porosity. The incorporation of zinc also drastically altered the electrochemical behavior of the cobalt hexafluoride. The energy storage capacity reached a maximum for the solid with a cobalt-zinc ratio of 3:1, with an increase in the potential for the redox process. Based on the result, a hybrid supercapacitor was assembled with a specific energy of 30 watt-hour kilogram at a power of 450 watt kilogram. Specific energy values of 7 watt-hour kilogram were maintained even at a high specific power of 5.5 kilowatts per kilogram. Additionally, the device retained 85% of its initial capacitance after 5,000 galvanostatic charge and discharge cycles. The characterization of the device with electrochemical impedance spectroscopy indicates that the resistance increment caused the observed capacitance determined during cycling, probably caused by positive electrode deterioration during cycling. And well, this is all for me, and thank you so much.